Mathematics is an invaluable element of economic analysis, and through your studies you will develop your aptitude for mathematics by considering its application to economic problems, all while gaining a solid understanding of social policy issues and government actions. Solve and analyze current economic problems. Mathematical economics gives you the skills to tackle issues in consumer behavior, interactions among producers competing for market share, macroeconomic outcomes, and international trade, and more. Understand and predict economic behavior. Leverage methods such as differential calculus, differential equations, and mathematical optimization to understand economic behavior. Build your career foundation. Courses in mathematics, statistics, economics, and econometrics will sharpen your analytical skills for an interesting career in industry or government, graduate work, and more. Mathematical economics is a method of economics that utilizes math principles and tools to create economic theories and to investigate economic quandaries. Mathematics permits economists to construct precisely defined models from which exact conclusions can be derived with mathematical logic, which can then be tested using statistical data and used to make quantifiable predictions about future economic activity. The marriage of statistical methods, mathematics, and economic principles enabled the development of econometrics. Advancements in computing power, big data techniques, and other advanced mathematics applications have played a large part in making quantitative methods a standard element of economics. Mathematical economics is a form of economics that relies on quantitative methods to describe economic phenomena. Although the discipline of economics is heavily influenced by the bias of the researcher, mathematics allows economists to precisely define and test economic theories against real-world data. Economic policy decisions are rarely made without mathematical modeling to assess their impact, and new economics papers are rarely published without some mathematics in them. Mathematical economics relies on defining all the relevant assumptions, conditions, and causal structures of economic theories in mathematical terms. There are two main benefits to doing this. First, it allows economic theorists to use mathematical tools such as algebra and calculus to describe economic phenomena and draw precise inferences from their basic assumptions and definitions. Second, it allows economists to operationalize these theories and inferences so that they can be tested empirically using quantitative data and, if validated, used to produce quantitative predictions about economic matters for the benefit of businesses, investors, and policymakers. Mathematical economics is the application of mathematical methods to represent theories and analyze problems in economics. Often, these applied methods are beyond simple geometry, and may include differential and integral calculus, difference and differential equations, matrix algebra, mathematical programming, or other computational methods. Proponents of this approach claim that it allows the formulation of theoretical relationships with rigor, generality, and simplicity. Mathematics allows economists to form meaningful, testable propositions about wide-ranging and complex subjects which could less easily be expressed informally. Further, the language of mathematics allows economists to make specific, positive claims about controversial or contentious subjects that would be impossible without mathematics. Much of economic theory is currently presented in terms of mathematical economic models, a set of stylized and simplified mathematical relationships asserted to clarify assumptions and implications. Broad applications include optimization problems as to goal equilibrium, whether of a household, business firm, or policy maker. Static, or equilibrium, analysis in which the economic unit, such as a household, or economic system, such as a market or the economy, is modeled as not changing. Comparative statics as to a change from one equilibrium to another induced by a change in one or more factors. Dynamic analysis, tracing changes in an economic system over time, for example from economic growth. Formal economic modeling began in the 19th century with the use of differential calculus to represent and explain economic behavior, such as utility maximization, an early economic application of mathematical optimization. Economics became more mathematical as a discipline throughout the first half of the 20th century, but introduction of new and generalized techniques in the period around the Second World War, as in game theory, would greatly broaden the use of mathematical formulations in economics. This rapid systematizing of economics alarmed critics of the discipline as well as some noted economists. John Maynard Keynes, Robert Heilbronner, Friedrich Hayek, and others have criticized the broad use of mathematical models for human behavior, arguing that some human choices are irreducible to mathematics. The use of mathematics in the service of social and economic analysis dates back to the 17th century. Then, mainly in German universities, a style of instruction emerged which dealt specifically with detailed presentation of data as it related to public administration. Gottfried Okenval lectured in this fashion, coining the term statistics. At the same time, a small group of professors in England established a method of reasoning by figures upon things relating to government and referred to this practice as political arithmetic. Sir William Petty wrote at length on issues that would later concern economists, such as taxation, velocity of money and national income, but while his analysis was numerical, he rejected abstract mathematical methodology. Petty's use of detailed numerical data, along with John Grunt, would influence statisticians and economists for some time, even though Petty's works were largely ignored by English scholars. The mathematization of economics began in earnest in the 19th century. Most of the economic analysis of the time was what would later be called classical economics. Subjects were discussed and dispensed with through algebraic means, but calculus was not used. More importantly, until Johann Heinrich von Thenen's The Isolated State in 1826, economists did not develop explicit and abstract models for behavior in order to apply the tools of mathematics. Thenen's model of farmland use represents the first example of marginal analysis. Thenen's work was largely theoretical, but he also mined empirical data in order to attempt to support his generalizations. In comparison to his contemporaries, Thenen built economic models and tools, rather than applying previous tools to new problems. Meanwhile, a new cohort of scholars trained in the mathematical methods of the physical sciences gravitated to economics, advocating and applying those methods to their subject and described today as moving from geometry to mechanics. These included W.S. Jevons, who presented a paper on a general mathematical theory of political economy in 1862, providing an outline for use of the theory of marginal utility in political economy. In 1871, he published the Principles of Political Economy, declaring that the subject as science must be mathematical simply because it deals with quantities. Jevons expected that only collection of statistics for price and quantities would permit the subject as presented to become an exact science. Others preceded and followed in expanding mathematical representations of economic problems. Much of classical economics can be presented in simple geometric terms or elementary mathematical notation. Mathematical economics, however, conventionally makes use of calculus and matrix algebra in economic analysis in order to make powerful claims that would be more difficult without such mathematical tools. These tools are prerequisites for formal study, not only in mathematical economics but in contemporary economic theory in general. Economic problems often involve so many variables that mathematics is the only practical way of attacking and solving them. Alfred Marshall argued that every economic problem which can be quantified, analytically expressed, and solved, should be treated by means of mathematical work. Economics has become increasingly dependent upon mathematical methods and the mathematical tools it employs have become more sophisticated. As a result, mathematics has become considerably more important to professionals in economics and finance. Graduate programs in both economics and finance require strong undergraduate preparation in mathematics for admission and, for this reason, attract an increasingly high number of mathematicians. Applied mathematicians apply mathematical principles to practical problems, such as economic analysis and other economics-related issues, and many economic problems are often defined as integrated into the scope of applied mathematics. This integration results from the formulation of economic problems as stylized models with clear assumptions and falsifiable predictions. This modeling may be informal or prosaic, as it was in Adam Smith's The Wealth of Nations, or it may be formal, rigorous, and mathematical. Broadly speaking, formal economic models may be classified as stochastic or deterministic and as discrete or continuous. At a practical level, quantitative modeling is applied to many areas of economics, and several methodologies have evolved more or less independently of each other. Stochastic models are formulated using stochastic processes. They model economically observable values over time. Most of econometrics is based on statistics to formulate and test hypotheses about these processes or estimate parameters for them. Between the World Wars, Hermann Wald developed a representation of stationary stochastic processes in terms of autoregressive models and a determinist trend. Wald and Jan Tinbergen applied time series analysis to economic data. Contemporary research on time series statistics consider additional formulations of stationary processes, such as autoregressive moving average models. More general models include autoregressive conditional heteroscedasticity, ARCH, models and generalized ARCH, GARCH, models. Non-stochastic mathematical models may be purely qualitative, for example, models involved in some aspect of social choice theory, or quantitative, involving rationalization of financial variables, for example with hyperbolic coordinates, and / or specific forms of functional relationships between variables. In some cases, economic predictions of a model merely assert the direction of movement of economic variables, and so the functional relationships are used only in a qualitative sense. For example, if the price of an item increases, then the demand for that item will decrease. For such models, economists often use two-dimensional graphs instead of functions. Qualitative models are occasionally used. One example is qualitative scenario planning, in which possible future events are played out. Another example is non-numerical decision tree analysis. Qualitative models often suffer from lack of precision. Critics caution that mathematical economics may obscure rather than clarify economic theory and create a false air of precision and certainty to both theoretical and empirical economics. Formulating statements about economic theories in mathematical terms must always depend on a painstakingly precise definition of the terms that are being treated as quantities in a mathematical model. Unfortunately, due to the inescapable fact that economic phenomena always involve subjective and unobservable elements that take place within the human minds of the economic agents under study, such a precise definition is never entirely possible in economics. This inevitably leads to ambiguities of interpretation and the fudging of factors that can't be readily fit into a mathematical or econometric model. Such ambiguity and fudging are exactly what the practice of mathematical economics purports to avoid in its quest to provide hard, precise answers to the questions of decision-makers and policy-makers. At best, this sharply limits the level of certainty that can be placed on the conclusions thereby generated and, at worst, sophisticated mathematics can be used to cloak fundamentally misleading results and conclusions. As a result, economists, and those who rely on them as experts and authorities, tend to gloss over these issues in the interest of confidence and certitude in pushing their preferred economic explanations and policy prescriptions. Thank you for watching this video.